So this point are corresponding exactly to this FMO trimer. This means that in this point we have B2 equal to 0. So we have the ratio of these successive trimers by, I mean that this point 0.044, which is corresponding to FMO prediction. So we have obtained numerically 5 trimer, I mean that ground and 4 excited trimers by using this zero range model and confine, I mean that the FMO picture. So in the next slide, we have, I mean that there is a result for tetramer, 2 successive tetramer connected to this ground trimer, B for n plus 1 excited minus B3 over B for n, and here we have B3 over B for n. Here, of course, if we, I mean that move in the x-axis in this direction, these are the point that we have the ground trimer, and this is the point that the first excited ground tetramer, excuse me. This is the point that the first excited tetramer appears, and this ratio is corresponding to, I mean that B for n over B3 equal to 4.6. So it means that in this, we have this y equal to 0, and according to the value that we have in this plot, we can predict this 4.6. So again, we decrease the, I mean that B3 over B for n, we can see in this point. The next tetramer excited state appears. This is corresponding to B for n, I mean that the ratio of the ground tetramer with respect to the first excited tetramer is 13.8, or the ratio of the B for n plus 1 over B3 is 4.6, or I mean that the ratio of 2 successive first and second excited tetramer is 4.6. So that's the point that the new, I mean that the tetramer appears. So
is there any significance that this 13.6 is 3 times 4.6, or is it just by chance?
No. This point you mean?
No, I mean the
this?
Yeah, that is 3 times 4.6.
Yeah, this is that we can see again in the next cycle. So we see here again that if I decrease this binding energy ratio, we can see in this point that the third excited tetramer can appear, at least numerically. We can see this is corresponding to the ratio of the second excited tetramer with the third is 4.6, and you see this number again is repeating. So
my question was because 13.8, that is exactly 3 times 4.6. Is this factor 3 of any?
I have not think in this way yet, so probably it would be interesting. So the point is that if we go exactly at this point, I mean that when we have B3 equal to 0 or B3 over B for n equal to 0, and B2 is also equal to 0, it means that we can have B3 is equal to 0, we can have infinite number of tetramer states below the ground trimer with the energy ratio about 140. So this is just a prediction that we can do for the ground trimer. Of course, this is not valid for the other state because we have the energy ratio that we have for 2 successive trimer is 550, so it cannot be in this range. So if we have a look to, yeah.
Probably you said it, and this is all for mu4 divided by mu3, like this 1.6.
No. This is for 1.6. We are increasing. This is for 21. And this should be equal to 80. So this is that we see the, I mean that the changing this 4-body regularization parameter with the 3-body, and we can obtain this plot. Of course, we have also the other result that I forgot to talk about that, and we can also see the next slide also. This is the result that we have from the hammer and platter for the positive scattering length. This is the corresponding result for negative scattering length, and this is the interpolation at the unitary limit. We have also the Deltuva result. We have also the stature result, and we have also shown that a very small change of the dimer binding energy, because this red line is exactly at the unitary limit, this red curve. So what about if we change the dimer binding energy to positive scattering length or to negative scattering length? So we see that if we change to positive scattering length, when for this dot, that this is where the B3 over B2 is about 500. So you see that this is a very small dimer binding energy. So there is a deviation from the B2 equal to 0. And the next dashed dot line is for 230, and this is for 50, the ratio of the B3 over B2. So that even changing the, not to be exactly at the unitary limit, can change the result or this scaling plot. Of course, we know that using this square root can show that, that the deviation of the result more visible for comparison. And this is also done for the, the negative scattering length for the visual state.
So
As it's, yeah.
before you continue,
Yeah.
so you're saying that there's an accumulation point of tetramers at the point where the trimer hits the 3-atom continuum. Is that what you're saying? When the trimer binding in?
This is just, the result that we have for the, unitary limit for B2 equal to 0. So I have not yet presented the result for negative scattering length.
So you're saying at the point where your three-body parameter is such that all states disappear, no, but how should I
No,
understand this?
it was just for this point, excuse me, that I say that when, okay, this plot R is for, this line is for B2 equal to 0. This point is also equal to B3 equal to 0. Of course, for this ground trimer, we can have infinite number of tetramers.
The limit is you're taking